And finally, the last little video in our series, our unit, talking about solids, liquids, phase changes, and heat associated with that. Let's talk about evaporation for a sec. If I think about all the millions and millions of particles in a small sample of water even, and if I can statistically analyze the average speeds of the water particles in a sample, say you have a mole of water, 18 grams of water, not very much, but enough to think about 602 billion trillion particles, then most of them would have the average speed. A few of them would have slightly less, would have the average, the root mean square speed, the speed of a particle with the average kinetic energy. But in any case, you'd have a distribution of speeds. The question is, in that sample of water, are all of the water molecules available to, quote, evaporate, change from a liquid into a gas without the addition of anything more than room temperature? And the answer is not exactly. Wouldn't you need to be at the surface of the water? Because if you're trapped in the bottom or middle of the water sample, then you certainly can't contact the air and imagine the gaseous, imagine the liquid particles escaping up into the gas phase. So the answer is you got to be at the surface of the water, and it sure does help that you have a little bit more than the average speed. So maybe what, 10%, 20% of the particles in this water sample have faster than average speed, as I've drawn to here. So some of those particles, if at the surface, can evaporate. We can relate this to interparticle forces, which we talked about earlier in this unit. Was it this unit? No, the unit before. Yeah, it was this unit. Yeah, right. Here's a demonstration. I'll do it for you sometime. Here I have some water and some alcohol and some acetone on in a gauze, and I measure the temperature as I pull them out of the liquid sample and let them begin to evaporate. And it's interesting how evaporation is a cooling process in the first place, but aside from that, one of these liquids evaporates more quickly than the others. In other words, whichever one has fewer interparticle forces and or is light enough not to notice, or is heavy enough not to be as highly affected by those interparticle forces. Here's a definition you probably should know. Volatility, another demonstration, but I'll show you in class. Volatility is a measure of a liquid's ability to escape up into a liquid. Liquid's ability to escape up into a gas, or it could even be a solid subliming easily into a gas. So if a solid or a liquid is volatile, that just means it has low interparticle forces in the sample, it melts or boils or evaporates easily, and has a high vapor pressure. Vapor pressure? What are you talking about? Let me show you. Wikipedia. Actually, oh, here we go. Here are 3 jars, canning jars of an acetone and an alcohol and a water. And if I fill them up to the same height with the liquid acetone, no. This is a liquid ether, I think, and liquid alcohol and liquid water. And I put the lid on and shake them up. Very quickly, the airspace above the liquid becomes saturated totally with as much of this liquid as it can hold. It turns out that this liquid evaporates very easily, and a lot of the liquid particles get up into the gas phase. We call that a high vapor pressure, or the tendency of that liquid is great to change from liquid into a gas. This is a lower vapor pressure, and this water has even a lower vapor pressure. You know that water is like the champ, interparticle forces and lots of hydrogen bonding, so that's what makes it so sticky and what allows it to evaporate so slowly. And if it evaporates slowly, it is not volatile, and if it's not volatile, it has a low vapor pressure. Boy, that's a mouthful. Here's a couple of diagrams looking at the liquids. Which one of these is probably water? Yeah, you got it. Water boils very, very hot and evaporates very, very slowly. So whichever curve heats up the slowest, and at about 760 millimeters of mercury and 100 degrees Celsius, that's where the normal boiling happens. And this is the normal boiling of some of the liquid. Maybe it's the alcohol. Boils at about 80 Celsius. This one boils at about 30-35 Celsius. And in any case, these lines are not linear. They're a little bit curvy. If I measure the vapor pressure, the push of the liquid to escape up into the gas phase, you know the answer to this question too. What evaporates more quickly, warm water or cold water? Have you ever seen steam rising up off a hot cup of coffee or hot chocolate or hot tea? Yeah, the hot liquid evaporates much more quickly, and the steam is sort of evidence to that evaporation. Let's look in a minute at how we could possibly use mathematics to analyze the curviness of these and perhaps even linearize them and get even more data out of it. I think I drew this red line here just to say that if I had this this diethyl ether liquid at normal room temperature and pressure, it's a liquid. But if I bring it down, it starts to boil. If I bring the pressure down, so I suck out the air from above this liquid just a little bit, the liquid starts to boil into a gas. Yeah, let's see. Let me enlarge this just a little bit here. Here I have four different hydrocarbons: pentane, hexane, heptane, octane, and based on interparticle forces, which one has the lowest vapor pressure? In other words, which one is the hardest to get to evaporate? And it's this one. The larger the particle, the more likely it is to be a liquid at room temperature. And if room temperature is about right here somewhere, then the pentane may just barely be a liquid. If I were to warm my room from, say, 30 to 35 or 40, at this normal pressure, it would start to boil pretty quickly. So I guess the pentane has a higher vapor pressure, lower vapor pressure, lower vapor pressure, lower vapor pressure, and this one even goes off the curve. Low interparticle forces, high interparticle forces. Interesting. Okay, back out again. Just one more of those, and then we'll look at the mathematics. Water, tetrachloromethane, pentane, a lot of interparticle forces, fewer interparticle forces, high volatility, high vapor pressure, low volatility, low vapor pressure. Pressure on this axis, temperature on this axis. So if I had a sample of 60-degree water at about 200 torr, it would be boiling. Interesting, you can boil water cooler than 100 degrees. Here's the Clausius-Clapeyron equation, the two-point form. Don't worry about spelling those dudes' names, but it's a way that they use to relate the vapor pressure of a liquid to its Kelvin temperature. Interestingly, the constant that allows us to relate these, the mathematics, is the reciprocal and natural log, but the constant involves the enthalpy of vaporization, the heat involved in vaporizing, which might make a little bit of sense because you might think that if I have a high heat of vaporization, then it would be hard to get it to evaporate. Yeah, I don't know. But anyways, this is the gas constant in energy units. Or if I look at just the normal slope-intercept form of the Clausius-Clapeyron equation, I put the natural log of the vapor pressure on this axis and the reciprocal of the Kelvin temperature on the x-axis, and look at the slope of this line. The slope of this line varies as the enthalpy of vaporization of that liquid. So in a tricky example, you might be asked the question, at 30 degrees Celsius, some liquid has a vapor pressure of 321 torr. That's 321 torr and 30 degrees Celsius plus 273 Kelvin. And increasing the temperature to 45 degrees plus 273 will raise the vapor pressure to 465 torr. So it's kind of tricky to make sure you get this one matched up with this one and this one matched up with this one. That is P1 and T1 and P2 and T2. But in any case, from there it's just simple algebra. I guess is natural logarithm algebra. A little bit of trig, but whatever. Just a button on the calculator, right? So take the natural logarithm function of this ratio, you get a negative value. This is a negative value over here because of that subtraction, and the enthalpy of vaporization, almost 20 kilojoules. So if I add 1 mole of this substance, and at its normal, almost ready to boil, No, I don't have to say that even, do I? If I had 1 mole of this substance and I wanted to vaporize it into a gas, I would say that. Make it at its boiling temperature, but still a liquid. Adding 20 kilojoules of heat energy to that would allow it to boil into a gas. Here's one for you to try. If you feel like pausing the video, it would be wise. Otherwise, you'll have to do it again later sometime with another question, but feel free. We'll see it in discussion and such, I think. 25 degrees, I have 100 torr vapor pressure. The enthalpy of vaporization, 33.5 kilojoules. What's the vapor pressure at 35 Celsius? Well, here we go. This time the unknown is the vapor pressure. The enthalpy of vaporization. There we go. Said it right. 100 torr is the vapor pressure at 298, or what is the pressure at 308? The gas constant is 8.31. Excuse me. Goodness. Frog in my throat today. Enthalpy of vaporization they gave to us. Make sure that this is in joules because that's in joules. I want the joules to cancel. And to get rid of the natural logarithm, do you remember you take the e to the x on this side and e to the x on this side? So e to the x on this side, e to the x on this side gets rid of the natural logarithm. E to the negative 0.439, 0.645, flip-flop 0.645 in the pressure, and you find 100. Hang on, sorry guys, there's an interruption. Sorry about that, took care of that. And so just algebra? Yeah, just algebra. But it's always tricky to find out. It's always easy to make little mistakes here or there. Try that with your calculator, see if you can get it. Thanks again, guys, and we'll see you sooner as opposed to later.